Okay, we worked by analogy to argue that the probability density in the Klein-Gordon picture is I h bar over 2m times psi star d psi dt minus psi d psi star by dt. Let's make this a little more compelling by noticing that the relationship between the time variation of a quantity plus the divergence of another quantity being equal to 0 is compatible with relativity. So if we have a 4-vector, now this is a generalization of this is not the divergence. Divergence is part of this more general object. So let's say we have T, a 4-vector TB, and we do the divergence, the 4 divergence of this 4-vector. This is, we're using the summation convention. Grad 0 T0, grad 1 T1, or del 1, del 2 T2, del 3 T3. These are spatial derivatives. This thing is, so that's a time derivative, d by dt of t naught, if we're using t. And then without specifying, this could be x, y, z, d by dx of tx, d by dy of ty, that's the divergence. So divergence contained in here of, well, we would call it t vector. And this thing, usually we'll see it like that. So this is the same kind of thing that we've seen before. And so we have a 4-vector TA equals T0, and then we have the other components which we can put in like that. And so this is the form that we've seen in the previous videos, and so it's compelling. It's a little more compelling that this component is the relativistic generalization that we found in the last video of the probability density. It's this object here. So we know that the solutions are free particles. This kind of a thing is a solution. E to the I k r, well, k dot r minus omega. Let's say we know this value. It's a positive quantity, omega star t, but we saw that we had a condition, a dispersion relation that relates the frequency, and we had a square root. So there are also solutions that look like this, e to the I kr plus omega star t. And so let's plug this into here, and let's see what we get for the probability density. We have I h bar over 2m times, we have, this could be a complex quantity, so we have we're building this, so we have an A star, complex conjugate of that. Then we do a derivative in time of psi, which gives us, well, let's do this one first. Okay, let's imagine this. That gives us minus I omega star times A minus A, we're doing this, I omega star rather, then we have, we're doing the psi star, we have an A star, so it looks like that, and this is I h bar over 2m times minus I omega star A modulo squared minus I omega star A modulo squared, and so this becomes 2 minus 2I omega star A modulo squared So we have a minus sign, but we have I times I, which brings in another minus sign. So we have h bar, we have a factor of 2, so we have h bar over m, a modulo squared. And these things are positive, so it looks like we're okay with this. There's nothing strange about the probability density. But now let's do the same thing for this object. If we do that, we have I h bar over 2m, a star, I omega star a minus a times minus I omega star a star, and this is I h bar over 2m, I omega star a modulo squared plus I omega star a modulo squared, and that is minus h bar over 2m. Sorry, there's no 2 there. Plus and plus, that's 2. We then we get rid of the factor of 2. So h bar minus h bar over m, a modulus squared. And notice that this is negative. So we have a strange feature here that we need to stop and think about, because we have a probability density that is negative.